Okay, right. So what are the free radicals? And here also, listen, here also we study same sequence. First, what is free radical? Next, preparation. Next, stability and structure, then stability. Then say, and most important is only stability. Other things, general concept is there, but the most important question can be expected from stability of free radical. Then the stability of free radical exactly similar to stability of carbocation. If you understand carbocation stability, it is exactly similar. Okay, so let's see. First, definition of free radical. Okay, so what are the free radical? That particularly carbon free radical. Say the organic compound in which carbon carry odd electron. So carbon carrying odd electron and having 7 electron in valency shell called carbon free radical. Therefore, what are the carbon free radical? The organic compound in which carbon has odd electron, means 1 odd electron, and having how many electron? 7 electron after sharing. Okay, then that is called carbon free radical. Therefore, the organic compound in which carbon carry odd electron, the organic compound in which carbon carry odd electron and having 7 electron in valence shell, and having 7 electrons in the valence shell called carbon free radicals. So they are denoted by like carbon 1 dot. Okay, for example, like methyl radical, comma, ethyl radical, propyl radical, many more can be written. Okay, next, preparation. How do you prepare? Yeah, free radical. So therefore, generally free radicals are prepared by homolytic cleavage of carbon-carbon bond, right? So next is preparation. So they are prepared by homolytic cleavage of carbon-carbon bond, CC bond. For example, let us take ethane. In ethane, okay, it may be carbon-carbon bond or even carbon-hydrogen bond, comma, carbon-halogen bond also possible. Right, it is ethane. In ethane, if it is treated with sunlight or diffused sunlight, it undergo homolytic cleavage. So we know that homolytic cleavage shown with half-headed fish hook arrow, which gives 2 free radical. Or let us take one more example. In methane, CH3H, it is treated with diffused sunlight, homolytic cleavage, it gives hydrogen radical and methyl radical. Okay, many more examples can be written. So this is how free radical can be prepared by homolytic cleavage. But we know that homolytic cleavage favored by, it is favored by what? Helper. So heat and electricity, light, pressure, that is peroxide and radical. Next is structure. So structure of carbon free radical. So what is the structure of the carbon free radical? See, generally the structure of carbon free radical is not actually, it is fixed, not predicted. Not it is predicted. Usually many free radical having planar, trigonal planar, but some free radical having even pyramidal also. So therefore the structure of free radical is not predicted, but usually carbon free radical, it means it has only carbon hydrogen, like methyl, ethyl, propyl, butyl, pentyl, etc. So these free radical having planar geometry, and if the carbon having electron withdrawing group like fluorine, chlorine, it is trifluoro methyl free radical which has pyramidal geometry. Okay, so let's see first methyl free radical or methyl ethyl similar free radicals. So here what is the hybridization and what is the geometry and bond angle. Tell me. Yeah, carbon having 3 bonds, it is like this, 3 bonds with the 3 hydrogen, okay, which undergo actually sp2, 1 2 3 bonds, but there is a one odd electron, free electron, which is on one orbital. Okay, so due to this one single electron, the geometry is supposed to be 120, but it is less than 120 comes, but some book given 120, let us take 120 only. Trigonal planar. Next, so geometry trigonal planar, and bond angle is 120 degrees. Okay, it is about carbon and hydrogen having radical, but if the carbon having more electronegative element like fluorine, chlorine, nitrogen, etc., then its geometry changes. Let us take CF3 dot, it is called a trifluoromethyl radical. In case of trifluoromethyl radical, its hybridization is sp, it goes sp3, hybridization sp3, and geometry becomes pyramidal, and bond angle changes, it is not given exactly, need not write, it is like this, not low, 1, okay, F, no, CF. Okay, so this is the geometry of the free radicals. Next is types of free radical. Okay, so types of free radicals. So what are the types of the free radicals? 1, methyl, 2, primary, 3, secondary, 4, tertiary. So this is a methyl free radical, this is primary free radical, secondary free radical, tertiary free radicals. These are the types of free radicals. Next is stability. The most important is stability. So stability of free radicals. Now tell me, before stability, first point, tell me whether free radicals are electrophiles or nucleophiles are, where we have studied. They have how many valence electron? 7. They have 7 valence electron, means less than 8, no? Less than 8, no? Less than 8 means electron deficient, electron rich, huh? Deficient. Therefore, free radicals are electron deficient, they are electrophiles. Free radicals, carbenes, you have written, carbocations, etc. They are electrophiles because they are electron deficient. Now, since they are electron deficient, they have less than 8 electron in valency shell. So, therefore, they are stabilized by electron releasing group, electron withdrawing group. They are stabilized by electron releasing group. Next, so that is the first point. Free radicals are electrophiles or electron deficient species. Next, whether they are paramagnetic or diamagnetic. So remember, wherever free radical comes, wherever odd electron comes, even chemical bonding also you have studied, the species which are having odd number of electron, they are paramagnetic. Therefore, these are paramagnetic. But what about carbocation, carbanion? Carbocation, carbanion are actually diamagnetic because they have paired electron. Right. So, carbocation, carbanion having paired electron, all electrons are paired, therefore they are diamagnetic, but this is a paramagnetic. Okay. Next. Okay. Next is here, since they are electron deficient, so which group can stabilize? Electron. So therefore, electron releasing group can stabilize the carbon free radical. Therefore, finally, what is the stability? The stability of free radical directly proportional to, yes, electron releasing group and inversely proportional to electron withdrawing group. So therefore, stability of free radical directly proportional to electron releasing group, inversely proportional to electron withdrawing groups. Okay. ಅದು ವಿಂಡೋ ಓಪನ್ ಮಾಡಿ ಪಾಪ ಹೋಗುತ್ತದೆ ಅದಕ್ಕೆ. ರೈಟ್. ಕ್ಲೋಸ್ ಮಾಡಿಬಿಡಿ ಮತ್ತೆ ಬರುತ್ತೆ. ರೈಟ್. ಸೊ ದೇರ್ ಫಾರ್ ಸ್ಟೆಬಿಲಿಟಿ ಆಫ್ ಫ್ರೀ ರಾಡಿಕಲ್ ಡೈರೆಕ್ಟ್ಲಿ ಪ್ರಪೋರ್ಷನಲ್ ಟು ಎಲೆಕ್ಟ್ರಾನ್ ರಿಲೀಸಿಂಗ್ ಗ್ರೂಪ್. Now tell me, what are the electron releasing group? Plus I group, plus M group and hyperconjugation. Okay. So these three are what? Electron releasing group. So therefore, now let's say factors affecting on stability of carbon free radicals. There are two factors. One, let us take resonance. And two, hyperconjugation. Resonance and hyperconjugation, these two are the factors affecting on stability of free radical. Let's study first resonance. Only two factors. Okay, no mesomeric effect comes here. Free radical does not undergo mesomeric effect. Okay, and no What do you say? Inductive effect is similar. Okay. Come on, tell me. So what is the effect of resonance in stability of free radical? Usually wherever resonance comes, it always stabilizes the molecule. Here also the stability of free radical directly proportional to, tell me, resonance or number of resonance structures. So therefore stability of free radicals directly proportional to number of resonance structures. As the number of resonance structures increases, stability of free radical is increases. Okay, when the resonance comes, we study two very important molecule, one allylic and benzylic. It comes throughout organic chemistry. So wherever resonance comes, we first study these two, allylic, benzylic. So let's say allylic free radical. Okay, this allylic free radical undergo resonance. So how this pi bond shifted here and this is comes here, so that CH2 become single bond, CH double bond, CH2. So how many RS? It is a 2 resonance structures. Next, one more example. Benzylic. Tell me. So benzylic free radical also undergo resonance. It form how many resonance? 3 plus 1, 4. It form 4 resonance structures. Then among allylic and benzylic free radical, which is most stable? Obviously benzylic is most stable compared to allylic. Okay, next here some important examples. CH2 double bond CH, CH2 tell me. So what is the order of stability of this? First is most stable, then second, then third, because number of resonance structures. Next, one more example. Let us take triphenyl methyl radical, diphenyl methyl, phenyl methyl, that is benzyl. Which is most stable? So triphenyl, methyl, diphenyl, then methyl, that is benzyl, right? Because of more resonance structures are possible there, right? Okay, so it is the resonance. Next, one more example. Let us take CH3, CH2, CH2 dot, CH2, CH, CH2 dot. Tell me, which is most stable? Both are primary only. Which is most? First one, allylic, right? Second one, allylic radical is more stable than, so simple alkyl. Okay, so next, second factor is hyperconjugation. Hyperconjugation. Okay, so what is the effect of hyperconjugation on stability of free radical? So usually hyperconjugation is a electron releasing effect. Electron releasing effect increases the stability of free radical. Therefore, stability of free radical directly proportional to what? Hyperconjugation. So as the number of hyperconjugation increases, what increases? Stability of radical increases. But to understand hyperconjugation, we'll study next topic that only. But here remember, first of all, which molecule undergo hyperconjugation? There are 3 molecules. 1 carbocation, 2 alkenes, 3 free radical. So carbocation, alkene, free radical, only 3 molecule undergo hyperconjugation. Condition is having at least one. So therefore, carbocation, comma, free radicals, comma, or alkene and alkene having at least one alpha hydrogen can exhibit hyperconjugation. Okay, so only 3 molecules having at least one alpha hydrogen can exhibit the hyperconjugation, otherwise not. Okay, therefore now we are studying free radical. Let us take CH3 comma CH3 CH2 dot CH3 CH CH3 C dot CH3 CH3. Come on, tell me. Let me tell first this. It can exhibit how many? It has how many alpha hydrogens? So this is a free radical carbon, alpha, alpha, alpha. There are 3 alpha carbon. Each alpha carbon has 3 hydrogen. Total 9 alpha hydrogen. Now here there are 6 alpha hydrogen. Here 3 alpha hydrogen. Here there is no alpha carbon, no alpha hydrogen. These 3 hydrogens are not alpha hydrogens. It is free radical hydrogen. So alpha hydrogen means there should be at least one carbon. On that carbon there is a alpha hydrogen should be there. Therefore here no alpha hydrogen. So therefore now tell me which is most stable? 9 alpha hydrogen most stable compared to 6, then 3, then no alpha hydrogen. So therefore now tell me the same thing we have studied in carbocation. Carbocation also tertiary is most stable, then secondary, then primary. So therefore you can take this is a tertiary free radical most stable, then secondary free radical, then 1 degree free radical and methyl free radical. Right? In the stability of free radical 3 to 1, 321, 3 greater than 2 greater than 1 greater than methyl. Okay. Right. One more example. Tell me which is most stable? 1, 2, 3. So all are tertiary? No. Tertiary free radical. It is tertiary. It is also tertiary. 3 are tertiary free radical. But which tertiary is most stable? So first one is most stable because there are 9 alpha hydrogen. So remember 9 alpha hydrogen is always most stable. Here is how many? 8 alpha hydrogen. Here is 2, 2, 2, 6 alpha hydrogen. Therefore Okay. Then in recent year, one question asked in JEE, the same we discussed. Let us take benzyl. In benzyl free radical, if there is a alkyl groups are present, so it is 1, 2, 3, 4. So what is the order of stability? Decreasing stability. So which is more stable? 2 na 3 ya? So all are carbon free radical, of course benzyl free radical. Then we need to say this group, electron releasing, it is electron releasing, it is also electron releasing. Okay, tell me, electron releasing group, they releases electron, they makes carbon free radical is most stable. Now question is, now which is a stronger electron releasing, either methyl group or tertiary butyl group? Tertiary butyl group, not, because hyperconjugation. You see now we discussed that it is alkene, no? Alkene carbon attached to adjacent carbon which is called alpha. This alpha carbon has how many hydrogen? 3 hydrogen. So it has 3 hydrogen, it means there are 3 hyperconjugation possible, right? Therefore due to hyperconjugation releasing electron is more. Then next is, here is there are only 2 hyperconjugation, 2 alpha hydrogen. So here is there is no alpha hydrogen, here 1 alpha hydrogen. So therefore wherever hyperconjugation is more, electron releasing effect is more stable. So therefore which is most stable? Second is most stable, then next is first is most stable, then fourth, then 3. So this is the order of stability of free radical. The same order we have studied in carbocation also. It is because of hyperconjugation. Then you may have doubt, there is a even plus I effect also possible. Plus I in all the case plus I effect possible. Due to plus I effect, of course it is electron releasing effect, stability increases. But when there is a hyperconjugation and plus I effect, which is dominate? Hyperconjugation is dominate. Okay, so it is a stability of free radical. Then now let's see overall stability or order of stability. Order of stability. Tell me, which is most stable? So triphenyl methyl, then diphenyl methyl, phenyl methyl, benzyl. Then after benzyl, which free radical is most stable? Allylic, right? Allylic. The next is tertiary, next is secondary, next is primary. Yes or no? Next is methyl. So therefore the stability of free radical exactly similar to stability of carbocation. Okay, but have we studied rearrangement of free radical? Where we study rearrangement? Only in carbocation. Otherwise, no, other than carbocation we won't get anywhere rearrangement, right? That's what this is. Next is, even if you take alkene, alkyne, tell me, then alkene free radical is more stable than alkyne free radical. The next is phenyl free radical, like similar to carbocation. The same order we have written in carbocation also, it is similar. Next is carbene. So what are carbene and preparation, its structure. So the concept of carbene you might have not studied in your plus 2, plus 1, plus 2 level, and it is important also. We will get it question from this. Okay, so what are the carbenes? See, carbenes are usually, they are bivalent, neutral bivalent species having 2 non-bonding electron. They are actually neutral and they are bivalent, means valency 2, but having 2 non-bonding electron. They are actually not lone pair, they are non-bonding electron. Then they are called what? Carbene. So therefore, carbenes are neutral, comma, bivalent species. Of course, carbon species having 2 non-bonding electrons called carbene. So therefore, in carbene you need to remember, first they are neutral, then they are bivalent, they are having 2 non-bonding electrons. Then how they are represented? Representation. So they are represented by like this. They are neutral and valency 2, bivalent, they have 2 bonds, and they have 2 non-bonding electron. They are actually not lone pair, we call non-bonding. I will tell you why they are non-bonding later. Okay, so then they are what? Carbenes. This is representation. Next is example. One like methylene carbene. It is called methylene carbene, CH2, 2 dots, comma, CCl2, 2 dots, it is called dichlorocarbene. This dichlorocarbene, it is actually electrophile, no? All the carbenes are what? Electrophile, right? They are actually electrophile, we have studied. They are electrophile. This dichlorocarbene, it is obtained where? In Reamer-Tiemann reaction. One of the important reaction we will going to study later. It is in Reamer-Tiemann reaction, no? Okay, next, even dialkyl carbene, or diphenyl carbene, etc. All these are bivalent. Okay, next is preparation. Okay, we have very limited example. One, carbene can be prepared from the diazomethane. This method we are going to study in P block element, preparation of dinitrogen, diazomethane. It is a diazomethane. On heating, nitrogen can be removed as a N2 gas and you will get CH2. It is a methylene carbene. Next, one more example from ketene. This is called ketene, methyl ketene, not ketone, it is ketene, methyl ketene on heating. So here this bond will be broken, you will get CH2 plus CO will be formed. This is also a carbene. Even in Reamer-Tiemann reaction, what is the reaction we used in preparation of this? Yeah, there is a chloroform. Chloroform reacts with KOH, that means base OH minus, right? This base remove the water or H, you will get a CCl2 dichlorocarbon, you will get in mechanism. It is in Reamer-Tiemann reaction. Next is types of carbenes. What are the types of carbene? So there are two types of carbene. One, singlet carbene. Two, triplet carbene. It is based on spin multiplicity. So based on spin multiplicity, they are classified into singlet and triplet. Okay, what is spin multiplicity? We study. Let's say first is singlet carbene. Okay, see here. In singlet carbene, it is actually CH2. Let us take CH2, methylene carbene. Right. In singlet carbene, the structure is like this: carbon, which is having two hydrogen like this, and there are two orbitals, 1 and 2. Okay. Then in case of singlet carbene, the two non-bonding electron present in a one orbital and they are paired. Only one point. In singlet carbene, there are two non-bonding electron. Of course, all are having two non-bonding. But how they are? In this carbene, two non-bonding electron present in same orbital and they are paired. They present same orbital and they are paired. Therefore, in singlet carbene, two non-bonding electron present in same orbital, two non-bonding electron present in same orbital and they are paired like this. Okay. Now tell me, if this is the structure, first is hybridization. What is hybridization? Then what is the bond angle? And next is what is the geometry? Next, CH bond length. Next is magnetic behavior, stability, then finally spin multiplicity. Okay. Tell me, first one, hybridization. So what is the hybridization of carbene, singlet carbene? We know that number of hybrid orbital equal to sigma plus lone pair. How many sigma? 1, 2. 2 sigma. See, in carbene actually two electrons are different. Okay, but here paired. Due to pairing, they become one lone pair. So therefore, 2 plus 1, it is 3. It means SP, yeah, SP2, right? SP2 hybridization and one lone pair. It is a bend shape now. bend shape or V shape, angular shape, sp2 one lone pair, angular shape. Next is geometry. No, bond angle we want, no. Bond angle you take 103. Bond angle 103. This is a bent or angular or V shape. Next is CH bond length. So what is the CH, this bond length? It is approximately 1.12 angstrom. The bond length will be same in singlet and triplet. And magnetic behavior, this is important. Tell me, what is the magnetic behavior? Either para or dia? Because of paired. Remember, wherever electrons are paired, dia. Unpaired, para. Therefore, this is a diamagnetic. Next, stability. So among, say, stability directly proportional to spin multiplicity. So stability directly proportional to spin multiplicity. Here singlet. Now tell me, what is the meaning of singlet? Spin multiplicity is 1. So then how do you calculate spin multiplicity? So spin multiplicity is equals to 2s plus 1. There is a formula called 2s plus 1 is a spin multiplicity. So therefore, now what is that 2 into s? S equal to what? Spin of electron. This is a clockwise plus half, anti-clockwise minus half. The spin of one unpaired electron is either plus half or minus half. Now if you take clockwise plus half, anti-clockwise minus half, plus half minus half, 0. That means 2 into 0, s value 0 plus 1 equal to 1. Therefore spin multiplicity 1, it is called singlet. The meaning of singlet is spin multiplicity is 1. That's what spin multiplicity directly proportional to stability. It is a spin multiplicity 1, therefore unstable. Okay, it is about singlet carbene. Therefore ultimately this sentence only important. In singlet carbene, two non-bonding electron present in same orbital and they paired. Because of this we will get this. Next, triplet carbene. Triplet. Right. In triplet carbene, see, it is opposite to this. In triplet carbene, there are two non-bonding electron, but two non-bonding electron not present in the same orbital. They present in two different orbital, that is parallel. Suppose one is clockwise, other should be a clockwise. If one is anti-clockwise, other should be a anti-clockwise. So therefore, in triplet carbene, two non-bonding electron present in different orbital and parallel. They are parallel. Okay. So if two non-bonding electron present in the different orbital and they are parallel, then what is the structure? Structure is like this. The two hydrogen bonds are like this, and there are two orbitals are like this. Okay. Then how two electron? They are parallel in two different orbital. Then now let's see what is the first hybridization. 2 bond angle, 3 geometry, 4 CH bond length, 5 magnetic behavior, important, 5 stability, then spin multiplicity. Okay. Now tell me, what is the hybridization? So number of sigma bond plus lone pair. Sigma bonds are 1, 2. Lone pair? No lone pair. They are actually free electrons, non-bonding free electron. So remember, non-bonding free electron, they does not involved in hybridization, right? So therefore it is 1 2, that means hybridization. So what is the geometry? Bond angle 180 degrees, 180. Then geometry, of course 180 is linear. Next, CH bond length, it will be same 1.12 angstrom in carbene. Magnetic behavior important, it is paramagnetic. So singlet is diamagnetic, triplet is paramagnetic. Question can be expected. Next, stability. Stability directly proportional to spin multiplicity. Tell me, what is the spin multiplicity? 2s plus 1. Then tell me here, 2 into s, s equal to 1. Why? There are two non-bonding electron present in same parallelly, no? If it is plus of, you will get 1. Therefore 1 plus 1, which is equals to 3. That's what is a triplet. The meaning of triplet is spin multiplicity is 3. And stability, compared to first one, this is more stable, because stability directly proportional to spin multiplicity. Okay, so these are the reaction intermediates. So far what we have completed? Cleavage of covalent bond. Next, attacking reagent. 3, reaction intermediate. Then fourth one is electronic effects, right? In electronic effects, again we have types of electronic effect. Write down first, electronic effects. Electronic effects. So what are the types of electronic effects? 1, inductive effect, or it is also called transmission effect. Inductive effect or transmission effect. 2, electromeric effect. 3, mesomeric effect. 4, hyperconjugation. It is also called no bond resonance. Hyperconjugation or no bond resonance. Okay. So listen, electronic effects. See, whatever we are studying now, these concepts are, they are actually backbone for organic chemistry. Organic chemistry is nothing if you understand this. If you understand this concept, the remaining things are like by hearting, memorizing things. The concept oriented question comes this only. And many students get do the mistake only in this concept, not reactions. Other things are conversions like interconversions, named reactions, mechanisms. That is can be understood if you know these things. Okay. Fine. Let us say electronic effects. So electronic effects are further classified into 4 types. Inductive effect, which is also called transmission effect. 2, electromeric effect. 3, mesomeric effect. 4, hyperconjugation, which is also called no bond resonance. Okay, first one, inductive effect. Right. So what is the inductive effect? So this is, we see very commonly in a organic molecule, if there is a carbon and having something more electronegative element, let us take X, Y, whatever it is. So this X has, suppose if it is more electronegative element, its electronegativity is more. Tell me, if the more electronegative element is present on like long chain carbon, so obviously what happened? It is in saturated molecule. We are studying in saturated molecule, that is alkane or haloalkane, like that. So therefore what happened here? This X has more electronegativity. Due to more electronegativity, it has tendency to take electron, right? Pull the electron. Okay. So therefore what happens? So there is the movement of electrons, that is called again bond movement towards more electronegative element, so that X gets partial negative charge and carbon gets partial positive charge, and this phenomena is called inductive effect. Right. Therefore now tell me, due to inductive effect, whether there is a partial displacement of electron takes place or complete displacement. It is a partial displacement. I am not writing that X is a plus and X is a minus, C is a plus. I am not writing. I am not writing complete positive charge, complete negative charge. Due to inductive effect, we write partial negative, partial positive. Therefore inductive effect is a partial displacement. Partial displacement of sigma bond or pi bond? Sigma bond, not pi bond. The partial displacement of sigma bond towards more electronegative element is called inductive effect. Right. So simple. The partial displacement of sigma electron towards more electronegative element, that is in saturated hydrocarbons. It should be a carbon-carbon double bond, not single bond, not double and triple bond. Then this phenomena called what? Inductive effect or transmission effect. So therefore the definition of inductive effect is partial displacement of sigma electrons, partial displacement of sigma electrons towards more electronegative element. Towards more electronegative element called inductive effect. Called inductive effect. Okay. Now let's see what are the characteristics of inductive effect. Questions based on characteristics is important, and even we can understand the question if you know the characteristics. Now what are the characteristics? One, first characteristic, tell me whether inductive effect is a partial displacement or complete displacement. It is only partial displacement. It is a partial displacement of sigma electron. 2, inductive effect is temporary effect or permanent effect? Is it temporary effect or permanent effect? It is a permanent effect. Why? See, this the displacement of sigma electron takes place as long as X is present, no? The displacement is not taking when something is attacking here. Now as long as molecule exists, the displacement continuously takes place. Okay. Therefore it is not a temporary. Temporary means, like for example here something Cx is there, here something something Y is added. When Y added, then only electron shifting takes place. When Y is removed, there is no shifting. Is it happening? And this is a permanent effect. See, remember, in all the electronic effect, only one electromeric effect is temporary effect, remaining effect are permanent. Right? Only electromeric, that is second one is temporary effect, that we will study later why. Therefore it is a permanent effect. Next, in this effect there is a polarity. Polarity will be produced, which is called polarization. The polarization of bond takes place is due to what? Either displacement of sigma electron or pi electron. Say here in CX bond, the polarity is creating, the polarity is producing. The polarity is producing because of what? Displacement of sigma electron. That means the polarization of bond. The polarization of bond takes place because of displacement of sigma electron, but not pi electron. Next is then tell me here in this inductive effect, is there any sigma electron changing the position? There is a dislocation of sigma electron takes place. For example, like carbon bond here, something X is here. So here there is a, of course, displacement taking place, but is it this whole sigma bond is coming to here? It means there is no displacement. The place of the sigma bond is not changing. It means electrons are not changing their orbital now. Here electron orbital is present here, the bond is here. These electrons are not changing the bond, that means orbital. Therefore, in this effect, there is no change of electron in the orbital. The electron will be present in the same orbital, but there is only partial displacement, right? That's also one of the important characteristic. And finally, then inductive effect. Inductive effect depends on the distance. It depends on the distance. How? See, as the distance of the carbon chain increases, it is decreases. As it is at fourth carbon from the more electronegative element. This is more electronegative element 1, 2, 3, 4. On fourth carbon, it is almost 0. It means inductive effect depends on the distance. As the distance from the electronegative element increases, then what happened? The inductive effect decreases and it becomes 0 on fourth carbon. On first carbon, it is a 1 positive, second carbon like 2 positive, not 2 positive, partial. So here 4, it is equal to 0. It means here 3 sigma, what is the T, 3 partial negative, this is very, very less. Don't think that number of, if the partial charge increases, not. It is less, this is more. So therefore, here it becomes 0. These are some important characteristics of inductive effect. Then inductive effect further classified into 2 types, plus I and minus I. Okay. So therefore, have written definition. Next characteristics. 1. It is a partial displacement of sigma electron. It is permanent effect, not temporary effect. 3. What is the third characteristic? It takes place, no, the polarization takes place, sigma bond, no, it takes place through the sigma bond. 4. Polarization takes place due to displacement of sigma bond. 4. In this effect, whether electron changes the orbital, so electron do not change the orbital. Electron will be fixed in those orbital, but there is a partial displacement will be there. Next, 6th one. Yeah, it depends on distance. Remember, inductive effect depends on distance, whereas mesomeric effect depends on position. We write different words. There we write position, here is distance. So it depends on distance, that is, as the distance from electronegativity increases as the distance from electronegative element increases, inductive effect is decreases and it becomes zero on which carbon? Fourth carbon. So it can be shown like this. Okay, if it is X, X is a more electronegative element, it is partial negative, partial positive, partial 2 positive, 3 partial positive, 4 partial positive, which is equal to 0. 1, 2, 3, 4. On fourth carbon, inductive effect become almost 0. Okay, these are the characteristics of inductive effect. Next is types of inductive effect. So what are the types of inductive effect? 1, plus I effect, minus I effect. 1, plus I effect. 2, minus I effect. So plus inductive effect, minus inductive effect. There are two types of inductive effect. Okay, so let us say plus I effect. Okay, and tell me plus I effect. Do you know what plus I groups are? Electron releasing, electron withdrawing? Electron releasing. Say for example, let us take methyl group. It is attached to CH2 plus carbocation. So what is the hybridization of carbocation? We know that it is sp2 and of course this is sp3. Can you tell me among sp2, sp3 which carbon is more electronegative? Obviously sp2 carbon has more electronegativity. Due to more electronegativity, what happened? The displacement of electron. Whether displacement of electron takes place, this is a substituent which is called a substituent. So displacement of electron takes place away from the substituent or towards substituent? Away from the substituent. That means towards more electronegative element. That means this is called plus I effect. What is a plus I effect? The displacement of sigma electron takes place away from the substituent is a plus I effect and group is called plus I group, right? Therefore, the displacement of sigma electron takes place away from the substituent, right? So therefore, if the displacement of sigma electron takes place away from the substituent, which is called plus I effect, and groups are called plus I groups. So therefore, now tell me, then group is called plus I group. Now this methyl is a plus I group. Now this methyl group is a plus I group whether it is electron releasing group or electron withdrawing group. So remember, plus I groups are always electron releasing groups. Therefore, plus I group is electron releasing group, or it is also called electron donating group. Okay, they are electron releasing group. Then tell me, what are the example for electron releasing groups? We have studied this example. Anyhow, once again write clearly. What are the electron releasing group? So remember, all alkyl groups, right? Irrespective, its nature, all alkyl, methyl, ethyl, propyl, whatever it is, all alkyl groups are electron releasing groups. Therefore, in all alkyl group, again which alkyl group has more electron releasing effect? tertiary alkyl. Tertiary alkyl is a more plus I group. The next is secondary, next is primary, next is methyl. So tertiary, secondary, primary, then methyl. Then among hydrogen, deuterium come first, then hydrogen. So therefore hydrogen is a plus I group, but its plus I effect is very less, equal to nil. That's what we take plus I, this hydrogen neither plus I nor minus I, it's almost equal to neutral. Okay, next is minus I groups. Tell me, what is the minus I effect? The displacement of sigma electron takes place. Okay. So displacement of sigma electron takes place towards substituent. Can you tell me example? So minus I effect is, let us take it is CH3, CH2 or Cl chlorine. Now tell me, in this molecule, now this is a carbon chain, now it becomes substituent. Don't confuse, here methyl substituent, you may have doubt. Here when you take methyl, here you can take ethyl substituent. Now here ethyl can be taken as a parent chain, chlorine substituent. Now this is a substituent, right? And obviously chlorine has more electronegativity compared to carbon. Therefore now there is a displacement of electron takes place towards substituent, right? The displacement of electron takes place towards the substituent is a minus I effect, and groups are called minus I group. Therefore minus I groups are what? Electron withdrawing groups. So minus I groups are electron withdrawing groups. Then let's see what are the important examples for minus I groups. So order is important, you must remember, right? Say in minus I group there is a NF3. NF3 plus is it has highest minus I effect, NF3 plus. The next is NH3 plus, next is CF3, next is NO2, next is CN, next is SO3H. Next is acid chloride, then aldehyde, ketone, next is fluorine, chlorine, bromine, iodine, OH, then OR. So these are the some important minus I groups. Right, remembering order also important, but majority question comes on this NO2, CN, SO3H and these. Question is like this: by giving these three, which of the following has more minus I effect? NO2, CN, like chlorine. So remember, NO2 has highest minus I effect, right? Which of the following has least minus I effect? Do you remember? Alkoxy. So when there is a alkoxy group present on benzene ring, this alkoxy group acts as a plus M, it is electron releasing. Their minus I effect is very less compared to plus M. That's what plus M effect dominate we have written, because here is least, its minus effect is least. Okay, then next, yeah, which is highest? NF3 plus. Why NF3 plus has highest minus I effect? One, usually nitrogen has more electronegativity. It has tendency to withdraw electron, take electron, right? Minus I in the sense it has to take electron, right? Withdraw. It has tendency to withdraw electron. Then along with this, and it is attached to 3-fluorine. 3-fluorine means it gets positive charge, as well as fluorine has highest electronegativity. Due to fluorine highest electronegativity, it withdraw electron from nitrogen, and nitrogen carrying positive charge, then its electron withdrawing power increases nearly 10 power 6 times, million times. That's what NF3 has highest minus I effect, right? So if there is NF3 anywhere, you can take that it is a highest minus I, because it alter many property, particularly acidic nature, basic nature. Okay, we will study later. Because of minus I effect, acidic nature is increases. That's what question is like this. There is a CF3 CH2COOH, and there is a NF3 and CH2COOH. Both are acetic acid, but one has CF3, another has NF3 plus. Then which is a more acidic? So minus I group increases acidic strength, right? We have studied, no? Electron withdrawing group. Electron withdrawing group increases acidic strength, we have studied. That means this is more acidic. There you will get this application. That's what order you have to memorize it. You have to by heart. I think this order you can remember easily. So you try this order. You must remember. Okay. So this is the minus I effect. Next is applications of inductive effect. So what are the applications of inductive effect? Take quickly. 1. Applications. 1. Reactivity of alkyl halide. 2. Dipole moment of alkyl halide. 3. Relative acidic strength of carboxylic acids. 4. Relative acidic strength of alcohol. 5. Relative basic strength of amine. And 6. Stability of carbocation and carbanion. See, this is we have studied stability of carbocation, carbanion due to inductive effect. We studied many more example, so that is need not to discuss. I will give 1-2 example. We have studied even acidic strength of carboxylic acid. Not carboxylic acid, we have studied acidic strength of acid. It is also acid, it is a base. This is also we have studied topic amine. In amine topic, whatever we have studied, we just revise here. Okay, that means 3, 4, 5, 6, these 4 covered, only 2. Okay, write quickly. First one, reactivity of alkyl halide. So what is the reactivity of alkyl halide? Say, alkyl halides are more reactive compared to alkane. Yes or no? Why? Reactivity of RX. Let us take methyl chloride and methane. Corresponding alkane is methane. Among methyl chloride, methane, which is more reactive? Of course, alkyl halide. So alkyl halides are more reactive compared with alkane. It is due to inductive effect. So here due to inductive effect, so here this carbon and halogen bonds get polarized. It means chlorine get partial negative, carbon get partial positive. So due to polarization of this carbon halogen bond, this bond can be broken so easily, right? Therefore alkyl halide or haloalkanes are more reactive compared to alkane. It is due to inductive effect. So therefore haloalkanes are more reactive than alkane due to inductive effect. Example, methyl chloride, methane. You can take any corresponding haloalkane. It's more reactive. Next, dipole moment. This is important. Dipole moment of alkyl halide. So what is the dipole moment of alkyl halide? Okay, tell me. Usually what is the dipole moment? Mu is equals to delta into L, where delta is the charge and L is the distance between the charges. Okay, what is the unit of dipole moment? D by. Okay, then dipole moment is either vector quantity or scalar quantity. It is a vector quantity. It depends on both direction and magnitude, right? This thing you have studied. Now let us see what is the dipole moment of alkyl halide or haloalkane. So remember, dipole moment dpm is directly proportional to difference in electronegativity. I'll take delta En. So dipole moment is directly proportional to usually difference in electronegativity. Okay, it means suppose the same question I think given today example. If there is a methyl fluoride, methyl chloride, methyl bromide, methyl iodide. So where the dipole moment is more? If you see the difference in electronegativity, fluorine carbon has more than chlorine, carbon, bromine and iodine carbon. But when you see the dipole moment order, so dipole moment order is methyl chloride is more compared to methyl fluor. Why? Anybody? Because of electron gain enthalpy. Okay, I have studied in where classification of element. Chlorine has more electron gain enthalpy compared to fluorine. It means dipole moment also depends on electron gain enthalpy. So because of that reason, so carbon chlorine bond has more dipole moment compared to carbon fluorine. Other things are same. Okay, this is one. Next, second point. As the number of halogen increases, what happens the dipole moment? Say for example, methyl chloride, dichloromethane, trichloromethane, carbon tetrachloride. So what is the order of dipole moment? It is decreases. As now this is applicable for only haloalkane. Don't apply to again your inorganic molecule. In haloalkane, as the number of halogen increases, chlorine, 2 chlorine, 3 chlorine, 4 chlorine, dipole moment is decreases, and here mu equal to 0. Then what is the reason that now generally as the halogen increases, we expect polarity increases. Dipole moment supposed to be increases, but not, because it is a vector quantity. No, it depends on direction. In case of chloromethane, there are 3 hydrogen, 1 chlorine like this, the bond movement towards chlorine like this. Next, if there are 2 chlorine is like this and 2 hydrogen is like this. So here bond movement, the bond movement towards this chlorine is some extent cancelled by this chlorine. Therefore this is more. If there are 3 chlorine, 1, 2, 3, 1 hydrogen, so you see the bond moment. Okay, so bond moment 3 is again cancelled more. If there is a 4 chlorine, that is in tetrahedral, so bond moment is mutually cancelled. So that's what, it's mu equal to 0. Now that is a bond what is it, dipole moment. Okay, next, even we studied dipole moment in di-substituted benzene, particularly chlorobenzene. The same example given textbook in NCERT textbook, second PUC. Okay, in case of dichlorobenzene, so the dipole moment in ortho and meta-dichloro, para-dichlorobenzene. So what is the order of dipole moment? So remember, dipole moment in para-dichlorobenzene absolutely 0 because it is mutually cancelled. Okay, here is not, see here is angle is, now how much it is? Around 60. Here is 120, right? Then para 0, then meta, then ortho. Then tell me, what is the relation between dipole moment and bond angle? It is called bond angle. Here 180, no? As the bond angle increases, dipole moment, it means inversely proportional. So therefore, dPm inversely proportional to theta. But the condition is what? There should be electron withdrawing group, not electron releasing. Condition is these halogens are electron withdrawing group. That means if substituents are electron withdrawing groups, not releasing. If the substituents are electron withdrawing group, dipole moment inversely proportional to theta. Okay. Next, one more. The same question is given inside. See, in organic chemistry, if you see the inside textbook, there are lot of questions are there. Even you do not find in any other books, but you can find very good question in inside textbook, particularly organic chemistry. There is one question. This question is given: chlorobenzene and chlorohexane. Chlorobenzene, chlorohexane. So which of the following has more dipole moment? It's a good logical question. Chloro. Okay, one hint is dPm is directly proportional to difference in electronegativity. Then Drishti yaudu? Hint is this. Chloro? Ida? Chlorohexane. So who said chlorohexane? Can you give reason? Okay, Uday. Very good. Say in case of chlorobenzene, chlorohexane, this is sp3, no? sp3 carbon, it's chlorine. And this carbon is what? sp2 carbon, chlorine. sp2 carbon has more electronegativity compared to sp3. Yes or no? So therefore, it has more electronegativity. Of course, it is also more. You see the difference. Now you see the difference here. sp3 carbon has less En. This is same. Chlorine, chlorine same. Therefore, where you get more difference? In chlorocyclohexane. That's what. Chlorocyclohexane has more dipole moment compared to chlorobenzene. This question given in NCERT textbook, second PUC. So therefore, dipole moment concept is important. Okay. Okay. Tell me. Symbol change ಮಾಡಬೇಕಾ? Okay. ನೋಡಿ, suppose ನೋಡಿ, this is electron withdrawing tane. If there is electron releasing group is there, you tell me now. See, you need not to be worry about dipole moment. You just try to write the structure so that you will get idea what may be anta. For example, if there is a methyl group here, okay, it is also methyl group. Okay, it is a methyl group here, it is a chlorine. Tell me, which of the following has more dipole moment? You see the electron transmission. Where the electron transmission here? Plus I, it is also plus I, no? Correct? How it is? In opposite, no? In opposite direction. Next here it is, right? Therefore, the bond moment is same direction, it is always additive. Oh, tane, the bond moment one direction is add agutte, opposite is cancel agutte. Therefore, this is more compared to this. ಅಷ್ಟೇ ಅಂದರೆ ನೀವು ಏನು ನೋಡಬೇಕು, ಬಾಂಡ್ ಮೂಮೆಂಟ್ ನೋಡಬೇಕು, ಎಲೆಕ್ಟ್ರಾನಿಕ್ ಟ್ರಾನ್ಸ್ಮಿಷನ್ ನೋಡಬೇಕು, ಯಾವ ಕಡೆ ಮೂಮೆಂಟ್ ಇದೆ ಅಂತ. ಇದೇ ಎಕ್ಸಾಂಪಲ್ ಕೊಡಬೇಕನ್ನೇನಿಲ್ಲ, ಬೇರೆ ಎಕ್ಸಾಂಪಲ್ ಕೊಡ್ಬೋದು. ಯು ಸಿ ಲೈಕ್ ದಿಸ್, ಸೊ ವಿಲ್ ಗೆಟ್ ಆನ್ಸರ್, ರೈಟ್. ಇಟ್ ಈಸ್ ಎ ಸೆಕೆಂಡ್ ಅಪ್ಲಿಕೇಶನ್, ಡೈಪೋಲ್ ಮೂಮೆಂಟ್. ಓಕೆ ನೋಡಿ, ಸಿ ದಿಸ್ ನೋ acidic strength, basic strength ಎಲ್ಲ, this actually comes in second PUC. We will finish here only. Okay, we shall continue next class.